Okay, so this is number 3 on the thin film interference lecture problem worksheet. So we have a camera lens. It appears greenish yellow, which is this wavelength, 570 nanometers, when white light reflects from it. So everybody knows white light has all colors of the rainbow, but this particular wavelength is shining the brightest in this problem. So it tells us the camera lens, it appears to be greenish yellow with this wavelength when white light reflects from it. What minimum thickness, which is this D right here, we're looking for the thickness of the film. We're given the index of refraction of the film, 1.25, and then we're given the index of refraction of the glass. So the glass is on the bottom, then we have this layer of film, and then we have air, like this. So what happens is, we're looking at this one particular color. Now look, are the other colors present? Yeah, and is it possible for the other colors to reflect strongly? It would be if we had a different thickness of the film. If there was a different thickness, then maybe red would be the brightest, or green would be, wait, this is green. Blue would maybe be the brightest. But we're focusing in on this one particular wavelength. So for starters, let's figure out what the wavelength would be in the film. Because as the light ray, so it's going to come in like this, it's going to hit this boundary. Some of it's going to reflect. Now, what do we notice right off the bat? It reflected. So the index of refraction up here is 1, and the index of refraction of the film is 1.25. What happens if a light ray reflects off of a medium that has a higher index of refraction? What's going to happen when the ray reflects off a boundary that has a higher index of refraction?
It's going to change phase.
It's going to change phase. So I'm going to put PC for phase change. Now what does a phase change mean? A phase change means, so let's say like right here, let's say that this ray comes in, and let's just say it's at a peak, okay? It's at a peak. So what's it going to be right there? The peak is going to instantly turn to a trough. All right? So peak turns to trough, for example. All right, then some of this incident ray is going to refract into the film, and it's going to get closer to the normal line, like that. Go do like this, and then here again, it's going to reflect. Oops, we got to make the angles the same. So following the law of reflection, angle of incidence equals angle of reflection. And then when it gets back to this boundary, it's going to refract, and then it'll be going parallel to this guy. Okay. Now, what happened at this boundary right here? What happened here? A phase change. How do I know there's a phase change? Because the index of refraction of the film is 1.25. The glass is 1.5. That's a higher index of refraction. So boom, this guy underwent a phase change as well. So that's 2 phase changes, which kind of cancel each other out. If you have 2 phase changes, it's like having no phase change at all. Does that make sense? It's like it went from peak to trough, and then this guy went from, peak to trough. So they both got flipped. All right. So let's find wavelength 2 right now. So what would this wavelength in here be? What you can do is you can say, we're going to go N1, wavelength 1 equals N2, wavelength 2. Where did I get that equation from? You can figure it out from this. N equals C over V, and V equals wavelength times frequency. By substituting those 2 equations together, you can get this equation. So N1 is 1, so wavelength 2 must be wavelength 1 over N2, so that's going to be 570 over 1.25, so wavelength 2 is 456 nanometers. Okay, now the extra distance traveled. So after refracting, this ray right here is going to travel an extra distance. It travels an extra distance before reuniting with this guy, right? Because this guy you know, boom, this guy comes in, reflects right away. But then this guy goes boom, boom, and we're just going to approximate this extra distance to 2d. Now, if they both underwent a phase change, if we want these to appear bright, so when somebody's eyeball is up here, get rid of this. So like somebody's eyeball is up here, and you're looking down, like there's an eyeball, right? You're looking down. If we want this to appear bright, what needs to be true about the extra distance? Is it going to be equal to a wavelength or wavelength over 2? Just a wavelength, because we've had 2 phase changes. They both underwent a phase change, because if we said wavelength over 2, that's like introducing a 3rd phase change, which would put them back out of phase again. It's kind of abstract, but I don't know. I don't think it's too crazy hard. So we want the extra distance traveled to equal wavelength, so therefore d must be equal to wavelength over 2. So the wavelength in the film is 456 divided by 2 gives us the thickness of the film at 228 nanometers, which is the answer.